All right, let me tell you a story. This is a high-stakes detective mystery, but our crime scene is a production server. We're talking about a mysterious failure that brought a high-performance system to its knees, and in solving it, revealed a deep, fundamental truth about how Node.js actually works.
So, picture this. You've got this awesome message processing system. In staging, it's a star performer. It's just chewing through 10,000 messages a minute, not even breaking a sweat. But as the quote says, production, well, that was a whole different story. A crisis was quietly building in the real world.
And this was the first sign of trouble. 2 full seconds of event loop lag. Now, for a system like this, 2 seconds isn't just a delay, it's a complete catastrophe. It means the very heart of the application was seizing up, and absolutely no one knew why.
Okay, so here's our mystery. The system is getting hammered with 50,000 messages a minute, and it starts failing in these really bizarre ways. You've got messages timing out, which then triggers retries, which then just makes the problem exponentially worse. The whole system was basically drowning in its own work. But here is where it gets super confusing. The engineers are staring at their dashboards, and the metrics are basically lying to them. CPU usage? A totally reasonable 60%. Memory? Rock solid. No slow database queries? Nothing. All the usual suspects? All the red flags? They were green.
So the team is just hitting one dead end after another. They're hunting for memory leaks, they're profiling the CPU, looking for hot loops, and they find nothing. It was like the application was spending all its time just waiting. But if it was waiting, why was the event loop lagging so badly? Something, somewhere, was secretly hogging the entire system.
And then, after days of this, the case breaks wide open. A senior engineer spots this suspicious little pattern in the code, a single, seemingly harmless line that was being called for every single message.
And this right here, this is the smoking gun. The entire system-saving fix was just changing this one line of code. Now, to a lot of us, this looks like swapping one way of saying run this later for another, right? They seem so similar. But that subtle, tiny difference, well, it was the key to everything.
The result was just, wow. Immediate and incredibly dramatic. Event loop lag completely plummeted, going from a disastrous 2 seconds down to a snappy 20 milliseconds. Throughput tripled. The system didn't just get better, it recovered instantly and started performing better than it ever had before. It was like a magic trick.
But here's the real kicker. The team knew what worked, but they had no clue why. Why on earth would swapping these two async functions have such a massive, system-altering impact? And this is where our little detective story turns into a deep dive into the very core of Node.js. So the root cause was a fundamental misunderstanding of how Node schedules work. See, the team thought all these async functions were basically created equal. They are not. The real culprit here has a name: microtask queue saturation. I know, it sounds complicated, but let's break it down.
To get this, we have to look inside the Node.js event loop. Just think of it like a factory assembly line. It has different stations, or phases. Most of the heavy lifting, network requests, database stuff, that happens in the poll phase. Our other key player, setImmediate, runs a little later, in the check phase. So where does our troublemaker, process.nextTick, fit in? Well, it doesn't. It's not a phase in the loop at all. It's what we call a microtask. Think of it as the big red emergency stop cord on that assembly line. When you schedule a nextTick, you're yanking that cord. The entire line grinds to a halt, and every single thing in this high-priority microtask queue must be cleared before the loop can even think about moving on. Now, setImmediate is completely different. It's a macro task. It doesn't pull the emergency cord. It's more like a scheduled quality check at the very end of the line. It waits patiently for its turn in the check phase, which happens specifically after all the main I/O work is done. It's cooperative.
So here it is, the heart of the problem. With 50,000 messages a minute, the system was scheduling thousands of these aggressive, high-priority nextTick microtasks every single second. The system wasn't blocked because the CPU was too busy, it was blocked because the scheduler itself was completely overwhelmed.
And this created the absolute nightmare scenario. The event loop got trapped in a vicious cycle. It would finish one thing, see this giant queue of nextTick microtasks, and start working on them. But, and here's the crazy part, each message it processed just added more microtasks to the very same queue it was trying to empty. The loop was literally running in circles, stuck before it could ever get to the next phase.
And this is the aha moment. All of the important stuff, the database responses, the network calls, the actual work of the service, all of that was waiting patiently in the poll phase, but the event loop never got there. It was being starved to death by a flood of what were supposed to be low-priority cleanup tasks, a classic, brutal case of priority inversion.
So, switching to setImmediate fixed everything because it moved that cleanup work to the check phase. This let the event loop finish its critical I/O work first and then deal with the cleanup. It brought fairness back to the system. And really, the source is right. The name is so confusing. If it had been called set after I/O, this whole mess probably would never have happened.
So the big lesson here isn't that one function is good and the other is bad. It's that as developers, we have a scheduler's toolkit, and we have to know exactly which tool to use for which job. Let's break down that toolkit.
Okay, this table is basically your cheat sheet. Process.nextTick, that's the nuclear option. You use it for supercritical, must-happen right-the-second error handling. setImmediate is your cooperative choice. You use it to defer work without blocking your I/O. And setTimeout with a 0, that's for when you just want to push something to the next full turn of the event loop.
And here's a huge warning for all of us writing modern JavaScript. You might be thinking, oh, I just use async await, so I'm safe. Not so fast. Under the hood, promises actually use microtasks, so a long chain of .ven calls can create the exact same starvation problem. Async await is fantastic for readability, but it doesn't let you off the hook for understanding how the scheduler works.
This whole story zooms out to a much bigger engineering principle. It's not just about writing async code. It's about building fair, cooperative systems and really understanding the real-world consequences when we get something like this wrong.
And those consequences were very real. 3 full days of senior engineering time completely burned hunting for a ghost in the machine. The company almost spent thousands of dollars scaling up their infrastructure, which, by the way, would not have fixed the problem. All of that because of one misunderstood line of code.
So the real takeaway for building robust systems is this. You have to treat the event loop like a precious, shared resource. Think like a cooperative multitasker. You need to classify your work by its true urgency, batch those non-critical tasks, and always, always think about the fairness of your scheduler.
And that really leaves us with one final, kind of provocative question to think about. I want you to look at your own applications, your own async code, and really ask yourself, is it helping your system be more responsive? Or could it be in some hidden corner, quietly starving it to death?